Good afternoon. As you already heard, my name is Indrek, Tallo, and my topic today is nanostructured tungsten carbide derived carbons as electrode materials for supercapacitors. Now, in the morning, you heard that carbide derived carbons can be used as material to build actuators. Actually, they are also used for constructing supercapacitors, and mainly they are being used as electrode materials. But since every different carbide derived carbon and also how it's made influences how the supercapacitors work, therefore all different carbides should be researched to find the best one that works the way we want to. And my presentation here is divided into three parts. First, I'm going to talk about how we make it, then about physical characterizations, which means what is it that we made, and also, in the end, electrochemical properties, which means does it work for us in our systems. And we used alpha tungsten carbide. The powder was particle size about 10 micrometers or less, and used this oven as a synthesized vessel. And the way the process works is that we heat it up in an inert atmosphere and flow chlorine gas through the system. And the chlorine reacts with the carbide and leaves carbon behind. And metal chloride, it's volatile, it goes to the neutralizer. And this is the simplified reaction that takes place. And we carried out the reaction in different temperatures from 800 to 1100 degrees. Now we come to the second part, which is physical characterization. And from X-ray diffraction, we can see that the material itself is mostly amorphous. There are some peaks in the diffractogram that are corresponding to graphitic material, but they are so very wide and so, let's say, not high that we can calculate that the material itself is very amorphous, and the crystallite sizes are very small, about 2 nanometers one way and maybe up to 5 nanometers the other way. And also we can come to the same conclusions when we look at the Raman spectrum of the material. But also what we can see from Raman spectroscopy that we couldn't see from the X-ray diffractograms is that at higher synthesis temperatures, the 2D peak, which comes out only in graphitic materials where the graphene layers are stacked together, starts to emerge. And also the crystallite sizes that are calculated from the disordered and graphitic peak from the Raman spectra also correspond to the crystallite sizes that were calculated from the X-ray diffractograms. Now also what this material looks like. The material that was synthesized at 800 degrees, we can see that it's mostly amorphous. like scrambled eggs. There are no graphitic lines that are visible, and also the selected area electron diffraction shows no rings that are specific to graphitized material. But however, when we look at the material that was synthesized at 1100 degrees, we can see some partly graphitized material. It's still mostly amorphous, but nonetheless we can see some certain elements of graphitization. And also from the selected area electron diffraction, we can already see the rings that correspond to graphite. And also we performed low temperature nitrogen sorption, and from that data we can see that isotherms are all type 1, which means that the material is almost all nanoporous. And we can see that slightly higher specific area is for does it work anymore? No problem, I have another one. So the material we synthesized at 1100 degrees. And also here are the results from sorption measurements, all in a graph. And what I'd like to stress out is the highest specific surface area for the material that was synthesized at 1100 degrees, and there is about 1580 meters per square gram. And also, when we look at the pore size distribution, then we can see that the material has narrow pores, but it also has some mesopores. And as we increase the synthesis temperature, the average pore sizes tend to shift a little bit to the wider pores. The shift is not very large, but it is still noticeable. Now, we know what the material looks like, but does it work in a way we want to, in an electrochemical cell? And for that, we load pressed it into electrodes, covered one side of the electrode with aluminium, and then constructed a test cell using this cosine core test cell. And the results. Well, we found that from cyclic voltammograms that the materials that were synthesized at different temperature all show nearly ideal capacitive behavior, and they don't vary much with synthesis temperature. They're all almost the same. And specific capacitance we got from these voltograms, we calculated it to be 120 Hz per gram. And also, this nearly ideal capacitive behavior was remained up to potentials 3.2. From there onwards, the current started to rise, and which indicated that some oxidation or reduction processes took place. And what was also very good with this material is that there was no deviations from this voltammograms, even in with a scan rate of up to 100 millivolts per second, which indicates that the ions in the electrolyte can move freely in the mesopores, and there was no starvation in the electrolyte. We also carried out some constant current peak charge measurements, and from these measurements we calculated round trip efficiency to be about 98% for all materials, and also we saw that again the synthesis temperature did not affect very much the capacitance of the material. And this is the measurements that we cycled it for 500 times, and we can see that capacitance did not drop very much. It stayed around 98 to 99%. We also carried out electrochemic impedance spectroscopy, and from the Nyquist plots we can see that the materials all behave very ideally for supercapacitors. They have quite low resistance in the high frequency area, and at the low frequency area the phase angle goes up to H9 90%. And also all these characteristics they neither depend much on the synthesis temperature or the potential that those Nyquist plots were measuring. And also from the impedance spectroscopy, series capacitance that were calculated, you see that about 0.1 hertz, the capacitance is about 120 to 132 farad per gram, which is about the average for carbide-derived carbons. And when we calculate it into the specific energy and compare it with other carbide-derived carbons, then we see that the material is quite average. We can store about 41 watt-hours per kilogram. But what is interesting is that when we compare the specific power, then the material we synthesize at higher temperatures, especially at 1000 degrees, it showed maximum power, specific power, which was about 2 times better than other carbide-derived carbons that were synthesized before and by other groups. So therefore we conclude that this material is very good if you want to get high power out of supercapacitors. And also we carried out some Ragona measurements which shows more like realistic process, like we would use those supercapacitors in real life, and we can see that the energy, this is constant power measurements, and if we have low power, then the maximum energy is between 30 to 40 watt-hours per kilogram, and specific power, we can draw this line here, goes to maybe somewhere around 100. And as a conclusion, the crystallinity as well as porosity depend only slightly on the chlorination temperature, and also the high resolution tunneling electron microscopy and X-ray, they show that there is only weak graphitization, and that's on the material that was synthesized at 1100 degrees. The ideal polarizability region is up to 3.2 volts, and maximum specific energy is about average. However, the specific power is about twice as what had been done previously. And based on these measurements, I can say that we have a very promising material. Thank you for your money.